Category Seminar at UNAM. Our speaker today is Tobias Fritz from the University of Innsbruck, who was nice enough to accept our invitation and who will be speaking to us about Markov categories. The title of his talk is Markov Categories, Probability and Statistics as a Theory of Information Flow. We will be reading questions from the chat during the talk. If at any point anyone wishes to be unmuted, please raise your hand and we will unmute you. There will also be a questions round at the end of the talk, and we will be reading questions from our live YouTube channel. So yeah, take it away, Tobias. Thank you very much.
Yeah, thank you. So it's great to be here, even if just virtually. And so thanks for the invitation. And I'm going to be speaking about categorical probability and more specifically, this recent approach of Markov categories, which is currently under development, and to be quite powerful in a sense that I'd like to explain and try to argue for. And besides the categorical slant, one thing that I realized in recently is that this kind of development also provides a new narrative for what probability and statistics, generally speaking, actually are. And so what I'm going to argue is that probability and statistics are in some sense a theory of information flow. It also comes out of the categorical development. All right, but so let me get the formal stuff out of the way, some references. And so far the list is relatively small. These are, at least from my perspective, the most important papers so far on the subject. So starting with a couple of papers by a Russian author in the 90s and early 2000s, who kind of introduced this framework of Markov categories already, and seems to have realized that its potential to some extent, but then I'm not sure for the reasons for why he hasn't been developing it further. And then independently of that, there was a paper by Cho and Jacobs appearing now 3 years ago in preprint form, which a lot of my talk is going to be kind of explaining definitions and results from that paper. Yeah, and then there's my own, a very long paper, which kind of developed this theory a little bit more systematically and proved some theorems in theoretical statistics within that framework. And then there's more particularly interesting is then maybe Eva Patterson's thesis, which is also pretty new, developing actually a correspondence between this theory of Markov categories and categorical algebra, and arguing that statistical models are analogous to models of an algebraic theory, and that there's a sort of can draw a correspondence with Lavier style categorical algebra there. And most recently, we've written a paper on a comparison of statistical experiments, and this is maybe interesting mainly insofar as that, as far as I know, this contains results which are not just new for categorical probability, but actually new for measure theoretic probability and statistics. So there we seem to have been able to do something which traditional methods have not achieved. All right, let me start with the technical details and just, well, actually start with a bit of intuition. And so many of us like to work with string diagrams, and just to set the stage, I mean, I'm sure you all know this, that morphisms or processes are drawn as these kind of boxes with, I'm going to use a convention coming from physics, with inputs or domains at the bottom and outputs or codomains on top. So sort of time kind of flows upwards. And so now we can compose these processes into networks. So here's the sort of usual kind of cooking or baking recipe. yeah, that we have a bunch of individual processes, and these take inputs like apples and flour, and then we apply the processes, we get certain outputs, and so then we get a network. And so this is a sort of, this is suitable for describing something like flow of actual materials in this case. But now suppose that we want to apply this in order to describe the flow of information. I mean, then one could think that, well, flow of information likewise can be described by these kinds of diagrams. And so now suppose that we want to describe a reason about flow of information in something like a medical trial. Have a patient or patients. Each patient has a certain state of health or medical condition, and then there's a treatment, but the outcome of that treatment is a function of both the medical condition or the health status and the compliance in the treatment. And that compliance itself is a function of the medical condition potentially. So here we encounter something which we had not encountered in this kind of formalism of flows of materials, in that the medical condition has an influence on both the compliance and on the treatment. And so this is a sort of copying of information. To reason about flow of information, it seems to have additional structure than just these kind of wiring diagrams, string diagrams, namely a kind of copying. And this is what's axiomatized in Markov categories. Okay, yeah, just to mention this again, that a theory of information flow needs additional pieces of structure. That we need this kind of copying, these copy morphisms, and also for deleting information, a morphism that takes an input and then produces no output. And so this results now, or suggests, the definition of a Markov category, that is a symmetric monodal category, so we can use string diagrams. Supply it, so this is a technical term that was introduced by Fong and Spivak, symmetric monodal categories with supply. In this case, what I mean is just that every object has a distinguished morphism. So every object X has a distinguished morphism to X, tensor X, called copying, and a distinguished morphism to the monodal unit called deletion, such that these form commutative comonads. And such that deletion is natural, and such that these interact well with the monodal structure. So this is a, well, if you're category theorist, then it's presumably quite obvious what that means, that the commutative comonad structure on a tensor product object is just the corresponding tensor product that you get when you also use the symmetry morphisms. Okay, and this last requirement, so this is equivalent to the category being semi-Cartesian, which means that the monodal unit is terminal. And there's argument or reasons also to relax this and not to postulate this. It's very convenient to use, but definition is maybe still a little bit and maybe we actually want to discard this. And then need to be a little bit more careful in reasoning, but then one has somehow greater generality. Okay, so yeah, Markov categories describe our sort of a theory of information flow. That's the basic idea. And so to talk a little bit about the semantics, in particular non-concerning probability, but there's other kinds of semantics too that I'll get to. So the paradigmatic example to have in mind is the category Finstock, so where the objects are just finite sets, and the morphisms are stochastic matrices. So that means the morphism from finite sets X to Y, to finite set Y, is a matrix like this, indexed by the elements of X and Y with non-negative real valued entries, satisfying this sort of normalization of probability equation. So we're supposed to think of, as the notation of y bar x indicates, we're supposed to think of this as the probability to get output y given the input x. So it's a kind of random map. And composition is then given by matrix multiplication, or which is known as the Chapman-Kolmogorov formula. So this is kind of the obvious thing that you would write down when you assume that the randomness contained in these two processes is independent, and so then that the probabilities multiply. So in particular, the terminal, so for the singleton set, a morphism out of that to some other finite set x is just then a probability distribution on x, because the indexing by x is trivial. Yeah, and so for a general morphism, there's many names. I'm going to call it Markov kernel because that's what the term Markov category comes from. It's supposed to be a category where the morphisms kind of behave like Markov kernels. And then this name is kind of doesn't suggest any particular interpretation. Unlike names like communication channel, then in Shannon's theory of communication, or probabilistic mapping, or information transformers. There's other names too. Okay, so now I've explained what it is as a category, but as a symmetric monodal category, so that the monodal structure is just given by, well, Cartesian product in objects, and on morphisms, this sort of, well, it's a tensor product of matrices, but probabilistically what this implements is then stochastic probabilistic independence, because we just multiply the probabilities when we do two processes in parallel. And so now the Markov category structure, the comonads, it's in the obvious maps that intuitively implement the copying of information, namely that on an input x, you get the outputs x1 and x2 with probability 1 if those are actually equal to x, and otherwise, well, you have probability 0 to get those outputs. And of course, the deletion maps must be the unique morphisms to the monodal unit, because that one is terminal. Yeah, so the normalization of probability here is what implements this naturality of the co-units and a terminality of 1. Okay, so this is a kind of paradigmatic example to keep in mind. And so then what I'm going to do in the following is to first state, you don't have the time to really go into details of proofs, some theorems, and at least concepts and theorems of probability theory in terms of Markov categories. Or at least I'll present one of those theorems that we have so far. And it's kind of surprising, at least to me, how many theorems one can actually develop just in this framework. And of course, this one would expect, I guess, as category theorists, in some cases that means turning theorems into definitions. Then I'll go say something about the vast landscape of Markov categories, that there are many that are not kind of probabilistic in any sense, but there's a couple of very general constructions. And my feeling is that in both of these aspects, in the development of both of these, we're still kind of very much at the beginning. And at least I personally have, for example, little intuition about what happens when you take one of these theorems and you instantiate it in one of these non-probabilistic Markov categories. What that results in so far, it's pretty much unexplored. And in some way, what I'd like to argue for is that there's some analogy to Topos theory here. I guess not, I mean, I don't want to claim that it has the same scope as Topos theory, but at least conceptually, and that these two aspects are similar to what happens in Topos theory, that every constructive piece of mathematics holds in every topos, but still there's and so there's a lot of theorems that one can develop, But still, there's also a big landscape of topuses, at least once you dig a little deeper and you actually, yeah, learn to know and appreciate more examples. And another analogy to topos theory is that also for Markov categories, there's a kind of hierarchy of additional axioms of differing strength. So in topos theory, we may have things like De Morgan topuses or Boolean topuses, where then more theorems hold. And also here, for proving some of the theorems of probability theory, one typically needs additional axioms than these just these bare ones. Okay, seems like no questions so far. So roughly my working hypothesis, and this is that this theory of Markov categories is a general theory of information flow, but also one can interpret it as kind of generalized probability theory and statistics, because what we're doing is proving theorems from probability and statistics within that framework. So if I kind of compose these two correspondences, I kind of want to argue that probability theory and statistics are a theory of information flow and conversely, in some sense. So another reference is actually that I hadn't listed at the beginning because there was no explicit treatment of these categories, is in Brandon Fong's master's thesis at Oxford, where he had shown how Bayesian networks can be interpreted in Markov categories without having defined them explicitly. So these are Bayesian networks, a kind of theory of causation, this causality and causal inference about how to infer causal mechanisms from observations. And he had shown that one can already do that, and this is the sort of connection between information flow and statistics. So yeah, but more generally, I think causal inference actually still remains to be developed in sort of the usual kind of theorems of causal inference, and this is one of the many open ends. Okay, but let me get a little bit to the details and showcase how these things work. And let's start with Bayes' rule and Bayesian, what's called Bayesian inversion. So Bayesian inversion is the prescription for how to compute conditional probabilities if, let's say, some y given x, when you're given the conditional the other way around of x given y. Well, then it's kind of trivial from following a trivial consequence of the definition of conditional probability, that you first compute the joint probability of both x and y happening. That's what this right-hand side is. And well, then you need to divide that by the probability of x in order to get that conditional. And now in terms of the Markov categories framework, this has this kind of representation. So if we look at the right-hand side, for example, here you can see that this variable y gets copied. There's two occurrences of y in there. And so in string diagram form, the right-hand side, which is the joint distribution of x and y, that gets represented like this. And correspondingly, the left-hand side is, it's pretty much the same, just with x and y exchanged. So then that looks like this. And so hence the definition of a Bayesian inverse, P of y given x, would be any morphism like this, which makes this equation hold. So we basically then use this to define conditioning or the Bayesian inversion in this case. And then one can actually show that whenever those conditionals exist, or at least in slightly more generalized form, then there's a sense in which this map, which the conditional is unique. So it's unique almost surely, and actually it's a dagger functor. So there's also some nice categorical properties here. So another concept, which is very important in probability, And I mean, every textbook, there's a lot of statements that certain things are not necessarily always true, but true almost surely. Or the for example, two random variables are equal with probability 1, meaning almost surely. And there's a surprisingly simple Markov category representation of this concept. And this is what it looks like. So let's maybe start with the case where A is just the monodal unit. So then P takes no input, but just P is, in that case, is just to be interpreted as the probability distribution on X. And in this case, what this says, so this is this intuition here, that F and G behave the same on all inputs that are produced by P. So on all values, on all elements of X that can occur, F and G must behave the same. This is basically what this equation is saying, because here we are copying the value of X and observing it as an output on the right. And the surprising thing is that this actually not only, so the intuition that I've just explained is what's true, I mean, in discrete probability theory and in Finstock in particular, but the surprising thing is that this is kind of also the correct definition measure theoretically, at least on the suitable assumptions and what kind of measures and measurable spaces one uses. Yeah, and now given this definition, it's kind of pretty straightforward to see how one can also relativize other concepts with respect to almost surely. So one of these other concepts is, for example, determinism. So as I had mentioned in the definition of Markov category, every morphism said, well, the co-units are natural with respect to every morphism, but in general, the copying maps are not, the co-multiplications are not. And so those which satisfy this naturality, which is this equation, those are called deterministic morphisms for the reason that in the semantics Finstock, this actually means that those more are deterministic in the sense of honest being honest functions, meaning stochastic matrices with entries 0 and 1. And I mean, this is, I mean, I'm not claiming this to be new. I mean, this goes back to Carboni and Walter's paper on Cartesian bicategories paper. But it's still, this kind of idea still applies here and gives a, is relevant. And so then it's quite straightforward to prove that these deterministic morphisms form, well, a monodal subcategory, but now because we have these natural comonads, commutative comonads and structures on all the objects, then the monodal structure is necessarily Cartesian, so it's a Cartesian monodal category. But in general, the monodal structure is not Cartesian, of course. So, another way to think about this is actually to say that F is independent of itself. This is, in probability theory, a common way to say that a probability measure only takes on values 0 or 1 if it's independent of itself. And this is another way to express what this equation says. And we take the definition of independence and conditional independence, and then we can instantiate it in this context, or to this kind of morphism is displayed here on the right. And then this equation would say that F is independent of itself, conditionally independent of itself. Yeah, and so here there's a general definition, also going back to Cho and Jacobs, their 2017 paper of conditional independence. And so this is kind of saying that F, the outputs of X and Y are independent given the input if you can produce those outputs, well, independently. You first copy the inputs and then let those copies independently produce corresponding outputs. And so the randomness contained in F sort of is applied independently already on the left because it is applied independently on the right. All right, so far this is kind of pretty simple, and these are just kind of basic definitions. So let me state at least one of the theorems that we've proven. And so this is sort of motivated by one of the fundamental theorems of probability, which is the law of large numbers, stating that when you have, let's say you have a sequence of real valued random variables. So imagine, for example, coin flips, just 0 or 1 or something. And we look at their average up to n. Then we take the limit of that as n goes to infinity. And then we can ask what is the probability of that limit actually being the expected value in the case where all these variables are identically distributed and independent. So the famous IID assumption. And so then the law of large numbers says that if these random variables are not sort of too, do not have kind of heavy tails, then this happens with probability 1. So the average will always converge to the expectation value, always in the almost surely sense. And so this is obviously something that if one wants to take categorical probability theory seriously, that we have to reproduce. And so far we have not been able to do this, but I have some kind of sense in how to go about it, but this is still open. But what we have been able to prove is closely related, and actually somehow in the traditional framework a more general result, which is this called 0-1 law due to Hewitt and Savage. And so the classical formulation is this: if you have a sequence, infinite sequence of, again, independent and identically distributed random variables, and then we consider any event A, which depends only on these, and is invariant under finite permutations, then the of the xi's, then the probability of that event is 0 or 1. So the theorem doesn't tell us which one it is, but at least we know that it's one of these two extreme cases. And so we can apply this to that situation of the law of large numbers. Sorry, I should not have said that this 0-1 law generalizes the law of large numbers, but it has at least a very similar flavor. What it tells us is that if we take now this convergence to the expectation value as the event A, well, then whether this happens or not is certainly invariant under finite permutations, because the convergence only doesn't care about what happens at finitely many i's. So the theorem tells us that this probability is 0 or 1, but unfortunately it doesn't tell us which one it is. Okay, so here's our version of the theorem, which reproduces this classical one in the context of measure theoretic probability. When we instantiate our version in measure theoretic probability, namely standard Borel spaces and Markov kernels, then it reproduces this one. So here the formulation is, I don't have the time now to explain all the concepts in here, all the relevant definitions, but I can try to at least sketch it. So the context is if we have a Markov category satisfying an additional what we've called causality axiom, and then, well, we take an object, not just a finite tensor power of it, but actually an infinite one. So this corresponds to having these infinitely many random variables here. And the infinite power is we just basically define it as the directed limit of the finite powers. So these finite powers form a directed diagram because the monodal unit is terminal. And so we kind of still have the projections that we would have in a Cartesian. So if these were finite products, we still have those projections, even if these finite powers are not actually products. But so that's why we can form this directed limit, and when that exists, and if it's preserved in addition by the tensor, then we call it a Kolmogorov power. And yeah, then the role of the joint distribution of these random variables for us is played by a morphism from an arbitrary object A to this Kolmogorov power. And then here we have this assumption of independent and identically distributed. Then this corresponds to this conditional independence here, that all of these factors, so when we apply these product projections, then basically we need to get conditional independence, as I had defined it before in a slightly generalized form. And then what generalizes this event A is that here we have a deterministic morphism from this power to some arbitrary other object. So in this context, this would mean that you can take the indicator function of A as the function as playing the role of the S here. So S is in general something like a statistic, which just takes your observations and turns that into a coarse-grained description of the relevant information contained in your observations. And so in this context, it would be the indicator function of A. Yeah, and then we have this invariance assumption under finite permutations. And so this translates into this, that both P and S need to be invariant under finite permutations acting on this Kolmogorov power. Yeah, and then the result is that the composite SP is deterministic. So yeah, this is maybe quite a mouthful, but so this again instantiates to this indicator function and being a deterministic function, and well, that exactly means that the event has probability 0 or 1 in this case. Okay, yeah, and so the proof is by string diagrams, but it's, at least to my mind, far from obvious. I had kind of posed this as an open problem, and I didn't know how to go about it until then my co-author on that paper emailed me about it and said that, hey, I found the solution, and then we ended up writing that up. Yeah. Okay, so this is just kind of to illustrate roughly how this kind of proving theorems within this framework works. And now I'd like to get to the other part of illustrating the kind of unexplored landscape of these categories. So one kind of general construction is Kleisler categories. And so what Kleisler categories of suitable monads, namely monads such that you get these commutative comonoid structures from the monad itself. And so the construction is that when C is a category with finite products, and you have a commutative monad on it, and that monad is affine, so the P of the terminal object is again terminal, then its Kleisler category is a Markov category in the obvious way, which means that the co-multiplications or the copy maps are just inherited from C, from just the usual diagonals in C, which has diagonals because it's a category with finite products. Yeah, and so this reproduces, for example, when you apply this to the Jerry monad, which is so the usual probability monad, going back to Lavier on measurable spaces, for example, then that gives a Markov category, or the Markov category for measure theoretic probability. One can also do this with other monads. For example, if one wants to have more topological aspects, then which is also often important in measure theory, then one can take something like compact Hausdorff spaces and radon, the monad of radon probability measures. And then one also gets a classic category as a Markov category there. Another one which is similar kind of flavor, but not strictly speaking, not about probabilities anymore, is if we take the classic category of the non-empty power set monad, just on set, so that the classic category is basically rel, just category of relations. Only almost, because now we have this only non-empty relations that are non-empty in one direction. And this is like the morphisms then are also kind of non-deterministic, but instead of probabilistic randomness and non-determinicity, we now have, well, non-determinicity more like in the actual and in the technical sense and how the term is used in non-determinism in computer science. And yeah, a bit more generally, it still holds when C doesn't have finite products, but it's just a Markov category itself. Okay, another general construction are categories of commutative comonads. And yeah, maybe this is not so surprising that then when you do this, when you start with a symmetric monodal category and you take the category of commutative comonoids in C, but now where the morphisms are not necessarily comonoid homomorphisms, but just co-unital maps as the morphisms. Then this gives a Markov category, because now every object comes by definition with a canonical co-multiplication. Yeah, and then those are that then is straightforward to see that results in a Markov category. So we're just kind of forcing it to be a Markov category. This must be some kind of universal construction, two-edge joint or something, but I'm not sure about the details. Okay, and so a nice example of this, which indirectly relates back to probability. So if we take vector spaces op over a field K, so in that case, the comonoids, or these, well, sorry, I should have written commutative comonoids here, correspond to commutative K algebras, well, because we've taken the op. And one can think of those algebras as somehow analogous or generalizing algebras of random variables. So those are like intuitively a little bit like multiplying random variables and adding random variables. And so this means that with the morphisms, then being basically unital linear maps, these are something like random variable transformers, meaning formal opposites of Markov kernels, or generalizing formal opposites of Markov kernels. Yeah, there's another very general class of examples, which actually also goes back to Lavier, as well, so many other things do, that one can treat already things like stochastic processes within the same framework. So if we have any category D as indexing diagrams as a shape category of diagrams, yes?
I don't think that's a question, I'm sorry.
Okay, yeah. So taking D as a category of diagram shapes and just C as a Markov category, then diagrams of shape D again form a Markov category if we restrict to deterministic morphisms in the diagrams, but not between the diagrams. That's a bit of a subtlety here. And so it turns out that if we take, for example, the integers as a poset, then one can interpret this as a category of discrete time stochastic processes, where the objects at time t correspond to sort of the measurable spaces that can carry information about the giant distribution of all the things that have happened up to time, no, sorry, yeah, have happened up to time t. And then the dimorphisms are just sort of projections that forget things that have happened at that happen at time t and only remember what happened up to time t minus 1. And this is kind of analogous to also what one does in probability theory to treat stochastic processes with those, one has those filtrations of sigma algebras. So those are basically already also diagrams of deterministic maps, deterministic Markov kernels. Yeah, one can also take as another diagram shape, instead of taking this kind of poset, one can take BG, so the one object category corresponding to a group G, and then one gets something more like dynamical systems or generalized dynamical systems with the group G as the time. And so this goes more in an ergodic theory direction. And so I'm actually keen to explore, but yeah, I don't think this has been done yet, but I'm really curious about how much ergodic theory one can develop like this. A little bit more speculative now, and this is now completely open, is that maybe there could be a Markov category that describes information theory. So I've mentioned measure theoretic probability, but then in a sort of different regime, there's information theory about entropy and conditional entropy, mutual information, and those kinds of things. And there's some well-known analogies between probability and information theory, but somehow it seems to be an open problem how to really make those analogies formal in the sense of how to obtain them as particular instances of a more general framework. And so, for example, one analogy is this analogy between conditional entropy, which has a formula like this, and conditional probability, which looks somehow formally analogous. And so I wonder if there's a Markov category for information theory, which might explain these kinds of analogies. But I'm not very confident about it, because I also have some reasons to be skeptical that it would explain this particular analogy. But in any case, I think it could still be interesting. So in that case, to get this would be a sort of asymptotic version of Finstock, for example, where the objects would be finite sets, and the morphisms, instead of just being maps, stochastic matrices like this, would actually be families indexed by n, and already sort of take a whole word, meaning n letters from the alphabet X, and output n letters in the alphabet Y. Because in information theory, we sort of look at a regime where many things happen at once, many things of the same type can happen at once, and so one would be interested in this kind of thing, and then modulo some kind of asymptotic equivalence. Yeah, and another example, or more like something which is between a class of examples and another potentially interesting theory development, is a categorical algebra for hyperstructures. So this is something that was suggested to me by Peter Arndt. He had noticed that one can maybe use Markov categories to, try and develop categorical algebra for what's called hyperstructures. So those are algebraic structures where the algebraic operations are not just single valued, but can be multi-valued, or actually probability distribution valued. And so, for example, in a category with finite products, a group G would be a monoid G, together with, we need to formulate the existence of inverses. And so it has this additional unit operations operations satisfy the usual equation that you copy a group element, and you take the inverse of one copy, and then you multiply them again, and then that's the identity in both directions. And so now the point is that this equation can be interpreted in any Markov category, where just for the black dot, we just interpret it no longer as a codiagonal, but now just as the structure morphism in a Markov category. And so now we can instantiate this in things like, well, the classic category of the jury monad, then we get these probabilistic hyperstructures, or in in something like this classic category of the non-empty power set monad, then we get more like these relational hyperstructures. And so more generally, one can consider models of any algebraic theory in any Markov category like this. I mean, this should be saying, I guess, hyper models. And yeah, so these are known as hyperstructures. And Peter's suggestion was to develop categorical algebra for these, which seems to be something that has that people who study these hyperstructures don't know how to do. Okay, so with that, I'm at the end, and I realize I haven't actually been looking at the time, so hopefully I'm not too far off. So yeah, Markov categories are an emerging formalism for providing something like a general theory of information. This should be saying, sorry, information flow. I realize I haven't actually put a lot of emphasis on this now, but the point was that in proving, when using string diagrams to prove those theorems of probability and statistics, well, one sort of more explicitly has a more explicit understanding of the information flow that takes place in those proofs, and also one naturally arrives at generalizations which are no longer necessarily about just probability measures, but are generally about Markov kernels, and therefore about information flow as well. Yeah, and many, at least qualitative results of probability theory seem to generalize to Markov categories. We already have a bunch, and there's others that are in progress. And what's open so far is to also generalize more quantitative results and proving, let's say, reproving something like the central limit theorem. That would be absolutely amazing. And I mean, so far I have no idea how to go about that. But even the law of large numbers, I think that would already be nice. And yeah, there's a large landscape which is so far unexplored, and which one can instantiate these qualitative results and theorems. And I've tried to argue that this is a little bit similar to Topa's theory. Okay, and yeah, in addition to the further directions that I've already mentioned, I think here's two more that I'm particularly interested in as well. So maybe let's look at a second one first. So I already mentioned that we'd also really like to get the quantitative results in probability theory. And so then obviously one needs some way of talking about those quantitative things. And so then it seems suggestive that we want to be looking at enriched Markov categories, but this has not been done yet. So meaning enriched in metric spaces and this kind of thing. Another big question that's on my mind is whether there is, and which is something that also computer scientists who study probabilistic programming have thought a lot about, this type of question, in terms of finding convenient categories for measure theoretic probability. So if you take, for example, just the classic category of the jury monad, it's actually not all that nice from the categorical perspective. So it does not have these conditionals in general. It is not, the deterministic morphisms forms a Cartesian category, but it's not Cartesian closed. And well, one can restrict the measurable spaces to the really nice ones, the standard Borel spaces. and then at least one has conditionals, one has, yeah, it's a little better, but it certainly still does not satisfy all of these things. And so far, I don't know of any category which would have all of these desiderata. And yeah, I don't even know if there is one. Yeah, any not even just measure theoretic probability, but I don't know any Markov category at all except for Cartesian ones, which are the boring ones. Yeah, okay, so with that, I'm at the end. And I think this actually looks pretty good as far as the time is concerned. Yeah, so yeah, thanks a lot.
Thank you very much, Tobias. Thank you very much for the very nice talk. Yeah, does anyone have any questions or comment for Tobias?
I don't know if I could start with my questions. Yeah. Okay, Tobias, thank you for a nice talk. Yeah, I have indeed 3 questions. I will do it together. The first is in TQFT. We know this hierarchy appearance of structures in TQFT, like vector spaces, Frobenius algebras, and then Hove algebras. And you work with these Markov categories has these common structures. So as very it's immediate to ask, what is you make this interpretation of the general theory of information flow and probability theory and statistics in terms of this Markov category. So my first question is in that, is make any sense to ask, well, what's happening if we have Frobenius algebra structure, Hove algebra structures, and so on, no? And well, my second question is more or less in the same direction. And this representation by Markov categories look like the open category conditions for a TQFT. So this makes sense, or like this variable.
What do you mean by the open category? Oh, yeah. You mean something like open, these open-closed TQFTs where?
Yeah, when we have this in dimension.
Where you have also kind of spatial boundaries.
Yeah, that kinds of things. Okay, it looked like more like that. Okay, that we have the brains, and the brains is like the variables, and then you have this. For example, when we have these equations by the probabilities, like we are in some space that joins these two the brains. Well, yeah, it doesn't matter if this has any sense, and if this has, could you make it precisely with objects and markers? Yeah.
Yes, yeah. I can try. Yeah, thanks.
Yeah.
So one thing that I.
Yeah. Well, and I have just one last question. Yeah, is in that you also work with this with the group as monoid, and yes, you make some. You say something about it, but I think, well, some of your diagrams, of your string diagrams, is like some algebraic conditions. So maybe is there some G equivariant version of the Markov categories?
Yes, yes, right, absolutely. Yeah. So let me try to say something about the relation to TQFTs, although I haven't actually thought about that much so far. So one thing that I can say definitely is that do you know about those hypergraph categories?
Yeah, you mentioned, yeah, and I see it, yeah, with monoids.
Oh, I see. Yeah, right. So those are categories where every object has well, does not just come with a distinguished comonoid structure, but actually a sort of Frobenius monoid structure, right? Or special Frobenius monoid, or I mean, there's a couple of variations on that, I guess. And so all of those are purely also Markov categories. And in particular, I guess that something like just a one category of cobordisms is also like that, right? Yeah, so certainly the pair of pans type constructions equip in particular every object with a canonical comonad structure, right? So in that sense, those are Markov categories, but I suspect that they're not so interesting as Markov categories. The reason being that these Markov categories have, or the theory of Markov categories is somehow intrinsically directed in terms of the information flow. That it really goes from bottom to top. So whenever you have a category with duals, I suspect that that instantiating this theory of information flow will not be so interesting.
Okay.
But in terms of the last question on the equivariance, yes, that's very much also something on my mind. And so what I've been hinting at here goes in that direction. That when you have a group G, and so certainly then when you take diagrams, so which are sort of, well, the category of objects with a G action, that forms another Markov category. But obviously it actually has more structure in just being a Markov category by, in particular, coming with a G action at a categorical level. And so one thing that I suspect is if we do this, for example, with the integers as the group, or the real numbers as the group, then we can develop something, not just probability theory and statistics, but actually a kind of theory, at least, or aspects, parts of the theory of stochastic processes. Because then we can explicitly also keep track of time. And maybe even, right, if we then generalize time to space-time, or, well, to space, to multidimensional sort of thing, maybe it can also give us something like a synthetic theory of, well, Euclidean QFTs then, I guess. But that's now extremely speculative. In the sense that stochastic processes just being one-dimensional Euclidean QFTs or statistical field theories.
But this about my second question about that, if this is an open category, that is the boundary of a TQFT. So,
yes, I'm not sure I understood that. Can you repeat that?
Yeah, so for example, when we have a TQFT in dimension 2, we can open the cover.
Yes.
Have a category of boundaries, and you take your objects of your category are the set of space or states, yeah, and then you go from one to another state. It's just to pass from states, but it's like a T15 dimension 1, yeah, more or less, yeah. But we have some condition like the Cardi condition and.
So are you considering that as just a symmetric monodal category, or is this more like a double category or monodal two category?
No, it's like an abelian category. It's just an abelian category.
Oh, an abelian category.
Yeah, for example, some in string topology.
Oh, sorry. So you're not talking about it at a level of the cobordisms, but at a level of the TQFTs themselves, then form an abelian. The open-closed TQFTs themselves form an abelian category.
No. So, it's like you take the space-time and then you choose, for example, some manifolds of your space-times, and these are like the set of states, and then, for example, take curves that join two states, two manifolds, and for example, you can take all the curves that, all the arrows that curves that go from one manifold to another manifold. You can take, for example, you quantize that space and you assign, for example, the homology or something like that. But this works as the different, and that like the category of states for a TQFT. So you just open your theory. It's quite different.
Yes, I mean, I know a little bit about this defect TQFTs, and then when you have, we can in particular have those boundaries, but I don't know what more to say about it that would be more specific to that setting in relation to my talk.
Yeah,
Sorry.
for example, one of your string diagrams, yeah, when you, for example, when you have this, your first equality in probability.
Which one?
Yeah, could you just come from the beginning? Yeah. 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 No, go ahead. That yeah.
Oh.
Yeah, for example, that when you go from in the line, yeah, but this F that travels along the paths is really similar to that when you change of the length.
Okay. Do you think you could point me to a reference or something, or to where I can? Do you think that the open closed TQFT analog of this equation is written down anywhere explicitly?
Yeah, also what I think is that the probability equations, yeah, maybe you have to introduce in your in the morphisms of your open category. Yeah. Well, it's just an idea.
Yeah, if you could point me to maybe to some literature where I could then maybe try to understand the analogy, or that could be helpful. Yeah.
Okay, so we have other questions. One by Robert. Maybe we can unmute him.
Okay, thanks. Well, first, Tobias, thanks a lot. It was a really nice talk, and great to have you here with us. So thank you. Okay, so let me try to ask some questions also, although maybe they go a bit far away. In part, you already talked about this a bit, answering Carlos' question about. So the first thing I'd like to ask you is about this aspect of time and time direction. So yeah, I'm particularly interested in connecting this to, let's say, descriptions of physics or physical systems, and more specifically to something that is called general probabilistic theories in foundation of quantum theory. So one thing there is what you already mentioned, that the formalism is time oriented. So the question is, but I'm not sure if you have more to say about this at the moment. If you think there's a way to get rid of this time orientation, and basically, get rid of the directions of the arrows in some sense. One thing I can say about this is that in a well related context, maybe in let's say general probabilistic theories, or what I call the positive formalism, what you have to do to be able to get rid of these directions is you have to drop normalization conditions. So in your case, this would be this condition that the probabilities add to 1. So basically, what you do is you relax this, and so what you were thinking previously of as being probabilities are no longer probabilities, but are some kind of relative or pre-probabilities. And only once you compose everything together and you take a kind of quotient, then you get actual probabilities. So I don't know if that's in any way related to things you have thought about So I don't know if you could comment on this maybe.
Yes, absolutely. So as far as physics is concerned, I have to say, and I think we're very much on the same page on that I personally feel like this kind of directionality is not adequate for doing physics because of the somehow inherent not just time reversibility in physics, but actually it's sort of time symmetry. And so this framework is not, at least to my mind, not intended to be applied in a physics context, but more like just for in probability and statistics, which does seem to have this intrinsic directionality. But so this being said, yes, one can get rid of that, and one can do undirected versions of this, and then I think that would exactly be these hypergraph categories of Phong and Spivak. And to some of the things that we've developed can be, well, yeah, as I mentioned, I think that the theorems themselves are probably not so interesting in those cases, because they use the directionality. But still, I think one can, some of the theory and some of the definitions can be maybe provide some inspiration for the development of those hypergraph categories. And so some of the axioms, I briefly mentioned this causality axiom, for example. This also seems to hold in many many hypergraph categories. So Brendan Phong, for example, told me that it does hold also if you do this with their so electrical networks, which are a hypergraph category, right? They don't have this directionality, but more like this time or this symmetry, more like this symplectic aspect to it. But yeah, and more of a probabilistic theories direction. I mean, general probabilistic theory is also, well, at least sort of in a more traditional setting that I'm still aware of, also have this directionality. Although I would also argue that they shouldn't have. But there I can say that another maybe relevant reference here is a paper which has developed quantum Markov categories, at least. So it's a quantum version of this, where the copying then corresponds basically to the formal dual of just operator multiplication. What Rob Speckens also calls analogical broadcasting. It's pretty much, yeah, it's exactly that. That's I'm not sure then how to go from there, from quantum to general probabilistic. And I don't know if it's possible, but at least for quantum, a quantum version of this does exist, and this is due to Arthur parsing that. He has a recent paper on these quantum Markov categories.
Okay, so in fact, you've already replied to the second question I was planning to ask. You preempted me with the quantum questions because I mean, a priori, if you look at the axioms and you say, well, you have this copying, then I mean, in quantum theory, you would be worried and say, well, we have a no cloning theorem and you cannot copy quantum states. So you have to replace this with something else. So you're telling me that people have thought about this already and there are already proposals. So I should really go and have a look at this.
Yes, exactly. Yes. And then kind of proposals or generalizations also of some of these definitions, like Bayesian inversion, for example. Then there's a quantum Markov category version of that. That's an author's main interest in this. Yes, to my mind, it feels somehow less natural than this classical version, because of then the interpretation of the morphisms is not just yeah, you cannot just take the completely positive maps, for example, because then again you run into the no broadcasting theorem.
Right.
but you need to relax that and just go to, I right now I don't exactly remember what kind of maps then he uses semantically. It's something like, yeah, more general linear maps between matrix algebras. Yeah. And then the multiplication, co-multiplication is just a formal dual of the operator multiplication.
Okay, so I really should have a look at this. Okay, thanks.
I can give you the reference or just, yeah, so it's, I assume you'd find it if you search for quantum Markov categories.
Okay, quantum Markov categories.
And otherwise, yeah, send me an email.
Okay, thanks.
So we have another question by Kevin Bouchot. Yeah, maybe we can unmute him.
Yeah, thank you so much for the talk. Had a question about like the like T-shaped Markov categories thing. So I was thinking if that part you have like the deterministic part to be part of the definition to make this construction, are there certain categories that, like certain Ds that we can take so that we don't have this condition, or does this fail like every time?
This fails whenever, as soon as D has any non-identity morphisms.
Okay. Would there be any like way of changing, or maybe like some different kinds of enrichedness or something that would maybe help this not happen?
I don't know, but actually I would argue that this is not a bug, so that this is not actually a problem, and that because it reproduces, for example, in the theory of stochastic processes, it reproduces also what people do traditionally. That a stochastic process is basically a probability measure on a filtration of sigma algebras. So on a measurable space equipped with an entire filtration of sigma algebras, and so this filtration is what keeps track of time, and so what takes you from one time to another is then just changing the sigma algebra, meaning it's a measurable map, namely the identity map, which just changes the sigma algebra, and so it's also deterministic.
Okay. Yeah.
So my answer would be that I think it's difficult to relax this, but for probability theory purposes, when also this is not a new phenomenon then, but reproduces the traditional thing.
Yeah, that's what I thought, but I just kind of wanted to make sure if there wasn't any weird way to make that not happen. Okay.
Yeah, right. No, I don't think so. Yeah.
Thank you.
The problem is if you try to allow non-deterministic morphisms in there, that then the copy maps are no longer actually natural transformations. Precisely because the failure of naturality for the non-deterministic morphisms. So you would have to change the morphisms of diagrams. Just forget about the naturality there. Maybe then it works.
Okay, thank you. Does anyone have any further questions or comments? Well, so
maybe I have a question. Do you have a mailing list or something for the seminar?
Sure, yeah, we can add you.
Yeah, please, yeah.
Yeah, I'll let you. So, yeah, I'll just write it down to remember.
Because I think I had wanted to attend last week's talk, but then I forgot it. Yeah, forgot about it again.
Yeah, so I have a question a bit related to Robert's and Carlos's questions. So yeah, so in the general boundary formulation for probability, so the version where you can compute probabilities and you can make probabilistic measurements. There is a way of considering time dependent regions. Sort of, they're not desirable, but yeah, you can do it.
Time dependent what?
So you can consider regions which are time dependent. Mm-hmm. You can consider a direction, and so I suppose if hypergraph categories would be sort of the analog of a general boundary formulation. So how do hypergraph categories relate to Markov categories? What are Markov categories to hypergraph categories?
Mm-hmm. So every hypergraph category is also a Markov category, because
well, yeah, sorry, I can't. Yeah, somehow my. Well, just a second.
Sure. Yeah. Maybe I can use let in some fresh air. So I assume we're waiting for Juan, right?
Okay. Yeah. Yeah. Sorry. He's coming.
You don't know what happened to him, right?
No, he's coming. Yeah.
Okay.
Yeah, sorry about that.
So you're there now?
Yeah, I'm sorry.
Okay, yeah. So every hypergraph category is also a Markov category, because you can just, well, forget the Frobenius algebra structure or Frobenius monoid structure in every object and just keep the comonoid structure around.
Yep.
Sorry, then it would be a Markov category without this normalization axiom at the bottom.
Okay.
But as I kind of hinted at, one can relax this and still prove many of the things, or slight generalizations of many of the things that I've mentioned. So in this sense, every hypergraph category is also a Markov category. But my feeling is that Markov categories are sort of a little different in their flavor and sort of the things that one wants to do with them. That a theory will not be very much parallel, but will be quite different.
Okay.
Maybe in a similar way to how, I mean, the theory of just algebras and Frobenius algebras is different or analogous.
Yeah. Yeah, with regards to the
and the hypergraph categories, I mean, as my personal feeling, this is kind of speculative, pretty speculative now, but my feeling is that one can also develop a lot of things for those. But I'm not quite sure exactly in which direction that would go, or what exactly to do with them. I mean, maybe one could take some of these theorems of probability and try to formulate kind of time symmetric versions, undirected versions of them, right?
Tobias,
yeah. Try to prove those in a hypergraph category setting.
Maybe, I don't know, but you mentioned this, that a Markov category is vector spaces. And for that, you take algebras evaluated in random variable. So maybe we have to replace the covariance category.
Replace what?
The covariance category. So we have to replace, because the covariance category is the initial object of a symmetric monodic functor that defines a TQFT. So maybe we have to change the geometric part of the TQFT and extend to something more, yeah, more general.
Interesting.
Yeah, but it's just
So you're. So I also take that as asking more like, what is the initial Markov category generated by a bunch of objects? Does that have a geometrical interpretation? So you're referring to something like the cobordism hypothesis theorem, right?
Yeah, more like this. Yeah.
I wish I had a slide now actually for the causality axiom. Yeah, well, I don't think I can say more about it, more about this at this point. But yeah, my feeling is that there's possibilities to do some analogous things for hypergraph categories.
Okay, thank you. So, Juan, do you have any other question? No, I think Juan have to go. Yeah, because the earphone is pregnant. So I think. Well, thank you very much, Toby. Es que Juan is mute.
Yeah, thank you. Yeah, I'm sorry about that. I have to, since I have to go back in, I have to be unmuted. Yeah, I don't think I have any more questions. I'm sorry. I think Robert and Carlos asked all the questions that I wanted to. Well,
yeah, sure. Thanks a lot.